Hi, I'm Steven Feuerstein, and I write practically perfect PLSQL.
Greetings and welcome to the PLSQL channel, a series of video trainings on the PLSQL language. My name is Steven Feuerstein, and I'm a PL/SQL developer just like you. This lesson is the latest in my rather extensive series on programming with collections, Oracle's array-like structures. The topic of this lesson is working with multi-level or nested collections, and I must warn you that it's among the most complicated features that I've ever run across in PLSQL, so I'll work on making it as simple and accessible as possible for you. So multi-level, aka nested collections. What are they? How do they work? How can you best put them to use in your application code? Well, first of all, a multi-level collection type is a type of array structure of collection whose element, that is, the value that sits inside each of its different rows, is directly or indirectly another collection. So I might have a collection of collections. I might have a collection of records. Each record contains a collection, and so on. Multi-level collections can be of any type: nested table, V-arrays, or associative arrays. And there are lots of different ways to utilize multi-level collections. Generally speaking, what you'll be doing is modeling normalized data structures in PL/SQL collections, essentially taking those different tables you have defined relationally and mimicking them in all their glory and all their complexity with multi-level collections. You can also emulate multi-dimensional arrays, though PL/SQL is probably not the best place to do complex multi-dimensional analysis. The syntax for working with multi-level collections can be really hard to parse in your head. Oracle obviously has gotten its handle around it. It can parse it and run your code. But it's going to take a while for you working with these complex structures to really understand how to utilize them and how to model your application data inside these collections. So let's take a look at a rather simple example, just introducing the basic concepts, the basic syntax. So what I'm going to be doing is working with object types, actually. So these are the object model within Oracle. There's something like classes and object-oriented languages. I'm going to create a vet visit. It's an object. And the vet visit has two attributes: a visit date and a reason for the visit. Just like you would create a table with two columns, here's an object type with two attributes. And then I'll create a table of object types. So this is a nested table of object types. So I have multiple visits to the vet. And then I'm going to create a pet object type. And a pet has several attributes. It has the tag number, so we can keep track of our pets, the name of the pet, what type of pet it is, the breed, and the pet care. What's the history of visits to the vet? So this object contains within it a list of visits to the vet. The visits to the vet is a list or a table of objects, the individual object information, visit information. Okay, great. Then I'm going to actually create a collection of pets. I have multiple pets. I need to keep track of all their information. So a bunch of pets is an associative array declared inside my PL/SQL block. Everything prior to this have been schema level objects. My object type is defined in the SQL layer. My nested table of object types is defined in the schema level, and as is my other object type. But my associative array is declared inside my PL/SQL block. So I've got multiple pets. Each pet is of this type. Each pet has within it a collection. So this is a multi-level collection object. Let's take a look at populating my pets number one. So my pets number one is, let's see, that's the first element of this collection, which means it has to be of this type pet. So I initialize that pet object type. I assign values for the different attributes. The tag number is 100. The name of the pet is Mercury. The type of the pet, the breed, is African gray parrot. And then I need to add a list of visits to the vet. So I call my constructor function for the vet visits list, which is a nested table of object types. Within my list, I declare or initialize and construct multiple visits to the vet. On the 1st of January, we got her wings clipped. On the 1st of April, we checked her cholesterol. Yes, it's true, you do these things for these big, expensive, smart birds. So this whole thing constructs a single element, a single object, that goes into my collection at the first location in my list. And it has within it another list composed of 2 different visits to the vet. Now, it's not always this complicated to construct, simply assign a value to a multi-level collection. It's this complex because I have these object types, but I thought it'd be a nice way to introduce this functionality to you if you haven't run into it before. So multiple visits to the vet goes into my vet visit lists. That whole thing goes into my pet. That pet goes into the first element in my list of pets. Let's take a look at accessing the elements of this complex structure. If I want to see the name of my first pet, I go to my collection, my pets, the first index value, dot name. Just like record.field, I do object type dot name. Let's say that I want to see the reason for the second visit for this to the vet for this animal. My pets 1 takes me to the first pet. Pet care is the name of the list of visits to the vet. That's a collection. So this whole thing is a collection. I go to the second location in that collection. This whole thing is an object type. It has as one of its elements or attributes the reason, and there's the reason. So one level dot second level dot attribute or field. If I just want to get the number of pets, that's just using the same old method. If I want to get the first visit to the vet, I would go to my pets 1, that's an object type instance, go to its list of visits to the vet, and ask for the first one. And if I want to, I can also make things a little bit clearer in my code. Instead of having a lot of hard-coded values, I could also hide the details. I could declare an object type instance as a variable, the first pet, and the first pet is my pets, and then find the first one. So this returns the first in the list. The last visit is, let's see, the first pet dot pet care. So this is my pet, the African gray parrot. This is the list of visits to the vet. Go to the last visit to the vet. Notice I have to repeat L first pet dot pet care dot last. And then I can see the reason for that last visit. So this gets me to the same place as this, but with less hard coding and demonstrating how you can create these intermediate objects or variables in your code to perhaps make it a little bit clearer as to what you're doing. Let's run the code. We'll ignore that. And there we go. So the name of my pet is Mercury. The reason for the second visit was to check her cholesterol. The number of elements in my list of pets is 1. The first index value is 1. And again, I asked for the reason for the last visit, check cholesterol. So it all works, and I bet you're looking at this code and thinking to yourself, this is really complicated. So here's my suggestion. You could stop right now, or certainly when I'm done with the whole lesson, go over this piece of code line by line. Make sure you understand how each element is defined. Again, if you're new to object types, that'll introduce another level of complexity, but there's nothing complicated here. It's just like creating a table with a bunch of columns, except it's an object type with a bunch of attributes. So make sure you understand the steps of the construction, and then make sure you can parse each one of these statements in your head and understand how they get the answer that they do. Then I would say you should continue on with this lesson, because it only gets more complicated from here. Okay. So that's an introduction to some of the syntax, the complexities, the fact that if you have a 2-level nested collection, you're likely to have 2 dots. If you have a 4-level nested collection, you'll have 4. X.Y.Z.Q. It can be very complicated, and you'll be seeing some examples like that. Let's take a look at another example, because definitely the best way to absorb what you can do with multi-level collections, how they work and what they look like, is simply to run through a bunch of examples. Now, back in my lesson on working with string index collections, I talked about the string tracker package, and basically I needed to keep track of the names of variables that I was using as I generated some code, because I didn't want to generate a declaration of the same name variable twice. So I built a package that would allow me to keep track of that information using a string index collection, allowing me to keep my code really, really simple. And that worked fine for a single list, and I'll show it to you in just a moment. But what if I needed to keep track of multiple lists and even lists within lists? Then that single list structure doesn't work very well, and it's a perfect opportunity to bring in multi-level collections. So what I'm going to do is extend that first version of my package to support multiple lists by using a string indexed multi-level collection, essentially a list of lists, literally in my code. Now, I don't need multi-level collections to do this. I could do it the hard way, and in fact, in the old days when Oracle didn't support nested collections, which was first introduced in 9.2, I did the things the hard way, just like this. In other words, I took one big collection, one big associative array, which can have up to about 4.3 billion elements in it, lots and lots of index values to choose from. And I would segment that one big collection. I would say, well, all the elements, all the index values between 1 and 10,000, that goes to list 1. List 2 is 10,001 to 20,000. List 3, whoops, sorry about that. List 3 is 20,001 to 30,000. I knew that my list would never get to be this big, so allocating 10,000 for each one would be fine. And so I could use one collection, I could assign different parts of my collection to different lists, and then I had to write fairly complicated code to manage the offsets. Well, if it's list ABC, that's from 20,001 to 3,000. If it's list 123, that's from 10,001 to 20,000. And the code was very complicated. I got the job done. But it was a hard way to use these data structures. And in fact, in general, that's what you want to be keeping your eye out for, and you'll see demonstrated in this lesson multiple times. If you find that the code is getting too complicated, if you're saying to yourself, it can't be this hard, there's got to be an easier way, then there usually is. And multi-level collections can be a really nice way to simplify your code, even if the resulting data structures that you define are more complex. So I don't want to do this. I don't want to build a lot of code to segment out a single list. I want to build the intelligence in the data structures themselves. Let's take a look. So first of all, string tracker 1. Just to refresh your memory, with string tracker 1, I want to mark a string as being used. And I want to be able to find out, is a string already in use? And what I did was create a list of, well, it doesn't matter, indexed by variable name. And what I did here was use subtypes and constants to hide the actual data types to make my code more readable. But the bottom line is, I'm going to index by the variable name, and the contents of the collection really doesn't matter at all. With my string index collection, all I had to do is the following. To mark a string as being used, take that string name, use it as the index value in my collection. The value that I assign to it doesn't really matter. It could be null, true, false, date, string, whatever. Doesn't matter because I never look at it. To determine if my string is in use, I simply ask, does this variable name, is this value you already used as an index value in this collection? So the exists method immediately tells me whether or not that string is in use. So this is an example of how I could use string indexing to greatly simplify my code. And again, if this is new to you, I urge you to stop watching this lesson now. Go back and watch the using string index collections. And you'll be able to then take much more advantage of this lesson, understand it much more easily. But that's my first version. And for a single list of strings, just keeping track of the list of strings I've used, it works really, really nicely. It's a very simple and elegant solution. As you can see, there's almost no code here. All the work is being done by Oracle and the collection definition. The problem is that's not good enough. I need to maintain lists within lists, multiple lists, all sorts of different stuff. So what I need to do is extend the definition of this package and what it does. Let's take a look at string tracker version 2. Now in the original version of my package, all I did was say mark the string as being used in the list. Is the string in use in the list? But if I have multiple lists, lists within lists, then things get more complicated. So I'm going to go back to my package specification. And I'm going to extend my API. I'm going to support the idea of creating a list. Pass in the name of the list, the description of the list, whether or not you want to override the existing contents of the list, and that will create a list for me. Then, I want to mark a string as being used in a particular list. I want to see if a string is in use in a particular list. So I have to add the list name to my parameters. So the package specification already exhibits the extension of functionality of this utility. Let's take a look at the package body. I'm sorry, before I go on, notice also that I create a number of subtypes. Subtypes are a great way to make my code more readable, to hide the underlying data structure. For more information about subtypes, watch my Stop or Say Goodbye to Hard Coding lesson series. So I declare a subtype called maxvarchar2, the maximum size allowed in PL SQL. I declare a list name type. I declare a value string type based on the previous subtype. And you can see them coming into play right here. Pass in my list name, it's of type listName T. Pass in my value string, it's of type value string T. So they self-document the value coming in, which is already pretty well documented by the name of the parameter. It's less important here than in the package body. Let's take a look at the package body. Now, all the code from line 15 to line 29 is nothing more than defining my multi-level collection structure. So as you can see, it's a fair amount of code, and there are even more complex examples that you will see. Let's take it step by step. In fact, I'm going to start from the bottom and work my way back up. I need to maintain a list of lists. For a given list name, I have elements in that list, and I can have multiple lists with different names. So I need something called, or of type, list of lists. What is a list of lists? A list of lists is a table of or collection of records indexed by the list name. So each list name is unique. I will use that as the index scheme into the list of values. That makes sense, right? Each element in this list is a record. So let's take a look at that. Each record for a list consists of a description field, which I pass in, and a list of values. Notice the name is not an attribute of my record. It's not one of the fields because it's the index value. It would be redundant to keep it here. So my list consists of the description, which is the maximum size possible, and a list of values. My list of values is another collection. This is a multi-level collection, clearly. And that list of values is the list of used elements. I want to keep track of the names that I've used. It's a table of, who cares? It doesn't matter. Happens to be a Boolean, but it really doesn't matter because I never look at the value. And it's indexed by the value string. So there's an example of a collection of records, which itself contains another collection, which itself is indexed by a string. So I have a two-level nested string indexed collection. And notice again that I've used my subtypes throughout. If I didn't, things would look a little bit different. So hopefully you can understand what I just said to you. Again, if it doesn't make sense, stop the video now and walk through those lines of code and ask yourself if you understand the construction of this type. Assuming you do, let's go back and take out these subtypes just to give you a sense of what happens when you don't use them. So I'm going to change my index by to my actual types. There's my 32767. Here's my Boolean. So this is what the code would look like without my subtypes. It's a table of Booleans indexed by varchar2. Wow, what does that do for me? If I write code like this without using subtypes, I need to put in a comment saying indexing by the variable name. Indexing by the list name. I need to document, I need to add comments just to make people understand the code that I wrote. Well, that doesn't make any sense. Don't write comments if you can use the code itself to explain what's going on. Let's go back to the original version. Now it tells its own story. It's a table of who cares, meaning it doesn't matter what value it is, indexed by the value string. It's a table of list records, indexed by the list name. So please make sure when you work with these complex structures to always use subtypes, constants to hide the values and hide the hard-coded types, self-documenting what you're doing. Okay, so I declare my variable list of lists based on this complex structure. Let's use it. Let's go to create list. Now, the example I'm showing you has a little bit too much of features, bells and whistles, for example. Do I want to override it, and so on. Let's just simplify things a bit. We're not going to worry about the overriding process right now. We're just going to look at the creation process for the list. So we get rid of that, it doesn't matter. I'm going to declare a local record of the type that's defined as one of my lists, table of list records. And the list record, in case you forget, has description and list of values. So I'm going to assign the description in to my description field of my list. I'll assign my list to the location in my array, my list of lists, defined by my list name. So the list name is my index value. I don't add sequentially to the list. I put it in directly for that list name. So that's an example of populating a list of lists. Now you don't see the list of values yet because I'm just creating the list. So right now it doesn't even look like a multi-level collection. You don't know, for example, from looking at this code, that the list record has within it another collection, but it does, and we'll see that in a moment. The main thing, though, is to understand how this assignment creates a new list. And in fact, I don't even need this intermediate list. I can simply do the following. So what I'm saying here is assign this description to the description field of my list of lists for this particular list. And in this one assignment, it'll automatically create the record, if it didn't already exist, with that location in the list, and then assign the value to the description. So you don't need these intermediate steps. It can just make things a bit easier on the eye when you have it. The record is assigned the description. The record is assigned to my collection. Okay, so that creates a list. Let's take a look at how I mark a list or a string is being used in a list. Here's the single assignment. I go to my list of lists. I go to that named list. This whole thing is itself a record of type list_rt. I go to its list of values, so record dot list of values. This itself is another collection, a collection of booleans. I go to the location in my list of booleans indicated by the value string. It's a string index collection. And I assign to it the value of doesn't matter. So again, I'm self-documenting that the contents of my collection in this case don't matter at all. What matters is the fact that I'm using up this location in my list, which has this name. So that single assignment takes care of everything for me. It marks this string as being used in this list. Now, when you first start working with these structures, and especially when you're working with somebody else's data structures that you didn't design yourself, parsing this kind of statement can be quite challenging. So again, if you want to, you could fully expand it. So what I'm going to do now is show you what it would look like, not as a single assignment, but as a series of assignments. So, get the record that's defined by that list name. There it is. There's my record. Get the list of values for that record and assign the value to that list. So this is a local variable that contains the current list of values for that list. I'm going to add doesn't matter to that list of values, but basically what I'm doing is assigning the location in the string. So I've added a new location to my list of values. And then I assign that list of values to the list of values field of my record, which is identified by that list name. So if you want to, you can go through all these steps, but really what you should do instead is make sure that you're comfortable with this logic, that you use named elements to make it easy to understand what they are, or easier to understand what they are, and then work with that single assignment. Finally, is a string in use? Pass in the name, pass in the string. And again, I'm going to be using the exists method to ask, does an element exist at that location? So first, does the list exist? Because if the list itself has not been defined, clearly no string is in use in that list. So if the list exists, then go to that list name in the list. This whole thing is, once again, a record. That record has as one of its field the list of values. This is a collection. And the question is, have I already used this string in this list of values? So I ask for exists on that string, and it returns true or false. And that's it. Now, if you want to, an alternative approach is I could have a single return statement, which you see here. And I say simply, go to this list, within this list of lists, and ask, does the element exist at that location? So a single return statement instead of all that other code. And what I'm going to do here is assume that the list name exists. If it doesn't exist, Oracle will raise the no data found exception, and I return false. You could certainly take this approach. The only reason that you might object to it is that we're essentially using the exception section as a kind of conditional branch. And it's not really a best practice to do that. So instead of burying that kind of logic inside the exception section, I keep it all in my executable section and simply ask first, does the element exist? If not, well, obviously, the string's not in use. Otherwise, use the exists for my lower level collection. The thing to remember here is that the exists method can only apply to that collection it's attached to. It can't also go up through your multi-level collections and ask, does this also exist in this collection? It doesn't work that way. So you have to ask it at multiple levels. One other little point in terms of the extension of this package is the idea of backward compatibility. And in fact, I need to finish what I was doing for backward compatibility. Let's just take a moment to copy in some code and explain to you what I'm talking about, because somehow I lost the part of this code from my package specification. So what I'm doing is adding back into my package specification 3 programs that support the original API. So remember, this is my first string tracker package. Mark is used, string in use, and there was no idea of a named list. It was just a single list. I went back to this existing package and I extended it. I added much more functionality, especially specifying the list name for the value string. The problem is that when I made this change, all the existing code that used a string tracker would have been invalidated. Well, that's no good. So what I'm also going to do is add some backward compatibility and then implement those simpler programs with an implicit list name that is declared as a constant in my package. In fact, it's declared as a non-printing character, so it's unlikely anybody would ever use it. The point here is that as you extend your packages, as you add more functionality, you always need to pay attention to backward compatibility as well. Okay, so that's a fairly complex structure. A multi-level collection, a list of records indexed by a string. Each record has within it a collection. That collection itself is indexed by string. Again, I urge you to stop the video, open up these files from your demo zip, play around with them yourself, make sure you understand how they're defined and how they work, and then you're ready to move on. Let's take a look at what's involved in emulating multi-dimensional arrays. Now, collections in Oracle are always single-dimensional. There's no way around that. You can't declare a 3-dimensional array in PL SQL. But a collection of collections, a multi-level collection, is kind of like a 2-dimensional array. It's not really the same, but it's kind of like it. And you can extrapolate from there. A 3-dimensional collection is a collection of collections of collections. And in fact, that's the example I'll show you, how you can define the emulation of a 3-dimensional collection. Here's the basic idea inside the declaration section. I need to declare a 3-dimensional array of strings. So my first dimension is a table of, list of, strings indexed by integer. My second dimension is a table of the first dimension. My third dimension is a table of the second dimension. It's really not the same thing as a true 3-dimensional array, but it's the best you can do in PL SQL. Let's take a closer look. This package was originally written by one of my co-authors, John Bereznovich, who's now a member of Oracle on the OEM team. So I give him all the credit. Now, when working with a 3-dimensional array in a 3GL language, like Fortran or C or whichever, you can specify an array as having a certain size, 3 by 5 by 100. It's a single declaration. and then you can reference it in a fairly natural way. So the typical syntax for referencing a three-dimensional array would be the array A, comma B, comma C, X, comma Y, comma Z. That's the typical syntax. That's not how it works in PL SQL. In PL SQL, again, I declare a multi-level collection. For every dimension, I need a collection level. So the third dimension is a collection of the second dimension a collection of the third dimension, the first dimension a list of strings. Anything defined of the dim3 type is sort of like a three-dimensional array. So what John did in addition to declaring this complex structure is also declare get and set programs. To set a cell value, I pass in my array my three dimensions and the value that I want to put in that X, comma Y, comma Z location. To get a cell value, I pass in my array and I specify my three dimensions and it returns the value. Let's take a look. Again, typical syntax, if I pass in my X, comma Y, comma Z, would simply to specify the first dimension, comma second, comma third, gets the value. That's the way you can do it in many other languages, not in PL SQL. In PL SQL, I would have to do something like this. Okay, array in, that's a dimension array of dimension 3, type 3. So that means that if I use the third dimension right here, this itself is a collection, since dim3 is a collection of collections. So that's a collection of collections. This is a collection. I go to that location in this collection, and this entire thing is a collection. I go to that location in this collection, and that is a string, so I assign the value to it. In the reverse order, I go to that location to get the cell value. I go to my array. I go to its third dimension. This is a collection. I go to the second dimension. This is a collection. I go to the third and last dimension, and this returns a string in the array. This is not very intuitive. Essentially, you're glomming together just index values. Notice there's no dots because there are no named elements. If you have a collection of records or a collection of object types, you have a named element like list of values. So then I can specify x dot list of values, collection dot list of values. When I simply have directly nested collections like this one, defined by this type, then the dots go away and I simply put together, concatenate together my references to my indexes. This is complicated not only because the syntax is unusual, but you have to remember the right order. For example, is it 3, 3, 2, 1 or 1, 2, 3? Which is why it's especially important when you build structures like this to hide the underlying complexity behind get and set programs, so the individual developer does not have to remember which order to supply things in. They just provide them by parameter name. So that's the emulation of a multi-dimensional array. Again, I urge you to stop your video, play around with the multdim package, try to create elements with it. In fact, if you look at the multdim test script, you'll find examples of using the set cell and get cell programs to set the values. So try it out, make sure it makes sense to you, and then proceed from there. Because proceeding from there is the last example, and it's the most complicated of all, and it involves a 4-level nested collection. And it's definitely the most complicated structure I ever built. And I used it to build a utility to analyze packages for potentially ambiguous overloading. Now what I'm going to do with this example is explore the implementation. I'm going to explain why I did it, how I did it at a high level, focusing on the multi-level collections and giving you a sense of the thought process I went through to get to my final implementation. It's way too complicated to try to explain fully in this lesson, and it would be much too long. Instead, what I did was write a 90-page series of articles, an 8-part article series that I published on OTN that explains this in great detail. Not only the nested collection side of things, but also the modularization that I needed to do in order to be able to understand what I wrote and explain it to others. To see this 8-part article series, visit stevenfeuerstein.com/read-Steven, or just go to stevenfeuerstein.com and click on the Read Steven. Here we go. Click on the Read Steven page and you'll see the link to the series there. So again, the idea over the next several pages is not for you to fully understand all the aspects of this implementation, just to get a sense of the kind of thought process you might go through as you start working with your own complex scenarios. And to reinforce the point I made at the beginning of this lesson, multi-level collections really do stand in as a kind of normalized database design. And in fact, that was specifically what I ran into in this particular example. And I found that coming up with the right model of multi-level collections, is it a 3-level collection, is it a 2-level collection, 14-level collection, is similar to normalizing data in relational tables. In other words, you want to go for the same objectives. I want to avoid redundancy. I want to accurately reflect the relationships between my data. And I want to simplify, that should be simplify the resulting application code. So let's take a look at an example. So first of all, the problem of ambiguous overloading. Strangely enough, it's actually possible to compile an overloading in a package that is not usable. Here's a package. The sales package has 2 programs called COL10. They each have a single parameter with the same name, and their data type is different, varchar2 versus car. Now, unfortunately, that's a difference, enough of a difference, the varchar2 versus car, to allow Oracle to compile this package without errors, which I think is a really bad idea because it turns out there is no way to actually call the program. Any way that I try to call the program will result in an ambiguous overloading, which means that Oracle can't figure out what to do. I'll open up that file. And you can run this yourself to take a look at the problems with ambiguous overloading. But the bottom line is that when I try to use these programs, I get messages like this. Too many declarations of calc total match this call. That's an example of ambiguous overloading. So if you're not careful, you can put these kinds of ambiguities into your code. Usually the ambiguity is not as extreme as this. You can't even use this package, not at all. No ability to use that package. Often it's more subtle depending on the fact that you have multiple parameters with default values, and if you leave off the default values, your overloading might become ambiguous. So anyway, I decided that this is a big problem and I want to help you. And I decided to build a utility that would automatically scan your package specification and identify ambiguous overloadings or the potential for them. Now, how can I do this? Well, one of the things I could do is write a parser of your PL/SQL code, parse this package, get out all the information about those programs and their parameters, and do my analysis. Well, I'm not a trained computer scientist. I'm a self-taught programmer. So building a parser for PL/SQL is way too complicated. And what I did instead was look around inside the Oracle Data Dictionary to see, is there a view that would help me get this information? And it turns out there is. It's called All Arguments. And All Arguments is a data dictionary view that contains information about all the arguments of all the procedures and functions to which I have access. Well, it seems like I should be able to use the All Arguments data to do my analysis of ambiguous overloadings because it has all to do with the arguments, the parameter list. Now again, I'm going to be showing you lots of links to files. I'm not going to be showing you and running all these files. I encourage you to do so on your own to learn in more detail how I had to work with all arguments and some of the challenges I ran into. And as I found, what is very common with a lot of the data dictionary views is that Oracle offers us a whole lot of pleasure mixed with some pain. In other words, a whole lot of really good data, but often not very well organized. And in fact, All Arguments is one of the worst defined data dictionary views I've ever seen. It's kind of bizarre in terms of how they structured it. It's very much denormalized, and it's incomplete. So I even had to complement my use of All Arguments with the DBMS describe package. Like I say, way too complicated to get into in this lesson. Let's just focus on the data structures and how I got to a 4-level nested collection. So I decided that I needed to use the All Arguments data dictionary view, grab the data from the view, drop it into a collection, and then work through the collection, the contents of the collection. So what I did was the same old, the first inclination, the first reflex, which is to grab all the data from All Arguments and dump it into a collection based on that view. That certainly is easy enough to do. So I declare an associative array, which is a table of rows from the All Arguments view that emulates the array structure. And then I can populate that array structure by querying all the data from all arguments for a given package, and dropping it into my collection of records. So this was really easy to do. It's a very powerful aspect of working with collections and collections of records. So I did that. And then I needed to start writing code. And what I found myself doing was writing lots and lots of really cumbersome, awkward, complicated code. For example, the all arguments data dictionary view, like I said, has denormalized data in it. So it has all the arguments for all the programs in all my packages in one view. Well, I need to pull out all the arguments for a given program. So what I found myself doing was writing loops through my big array and asking, well, if the current object is not the same as my last object name, then my program name is changed. Therefore, I need to start up a new analysis. And even within that list of programs, even within a program of that name, I had to worry about the overloading. I might have multiple programs with the same name. That, in fact, is the scenario I'm looking for, ambiguous overloadings. And I needed to find out, well, is my overload number different? And if so, then I'm starting with a new overloading, so I do new stuff instead of the same stuff. The bottom line, without trying to explain all the details here, is that I got seriously alarmed by the complexity of code I was writing. And I stopped myself and I said, Steven, if you're going to build this utility, you've got to figure out a better way. There's something wrong here. You made a left turn when you should have made a right turn somewhere along the way. So that's what I did. I took a step back and I realized that the problem is that the all arguments data dictionary view is one view, but it has multiple levels of information. Each program has one or more, zero or more overloading. So a program might not be overloaded, or it might have multiple programs with the same name. Each overloading has n arguments. One of my overloadings has 2 parameters, another has 3 parameters. Each argument itself can even have multiple levels of all argument data, because if my parameter is not scalar, if it's a record or an object type, then all arguments data dictionary view actually contains information about each individual field or attribute within that argument. Here's what it came down to. I have multiple programs. Each program can have multiple overloadings. Each overloading has multiple arguments, and each argument can have multiple breakouts. That's the actual structure of the all arguments data dictionary view. It's not a single view. In fact, it should be like 4 different views. Okay, so what do I do with that? I went back to my definition in my package, and instead of having a single collection of records, instead I created a 4-level nested collection to mimic the structure that I saw right here. Let's start from the bottom. First of all, my programs are organized by name. So I have a collection, an associative array indexed by the object name, the program name. And it's a list of overloadings of that program. Each overloading has an overload number, so it's indexed by integer. And it's a table of the arguments for that overloading. Each argument or parameter has a position in the list, so it's indexed by integer. And that has a table of breakouts. The breakouts are the actual rows in the all arguments table. For a scalar parameter, it's a 1-to-1 relationship. There's one breakout per argument. But for non-scalars, I might have multiple rows of information for a single argument. So there's my 4-level nested collection. And once I made this change to my 4-level nested collection, I found that it was, first of all, really easy to populate this complex collection. It looks like it'd be really difficult, but it wasn't at all. So originally what I did was assign my record to my single level collection of records. That was certainly easy enough, and I added it sequentially to the list. But now what I'm going to do is take that same record and I'm going to add it to my 4-level nested collection. So I use my record object name to specify the name of the object. My record overload is my overload number. The position is the position within the list, and the data level is my breakout level. So with this single assignment, it automatically populated across 4 levels of my nested collection. I didn't have to write a loop, loop within loop within loop. It basically did it all for me automatically, and essentially did a select distinct on program names that have results. So it automatically distributed the data out across all 4 levels of nested collections. It's a really, really nice, powerful statement that hides a lot of work. So there it is. One assignment populated my 4-level nested collection. Oh, and just a little comment here before I go on. The CC SmartArgs is the package body that I built as a part of this big utility that does this kind of operation, does the assignment. It's of course a bit more complicated than this, and you can take a look at the load arguments procedure to get a sense of the more complexity, the higher level of complexity involved. But at its core, what I'm doing is that single assignment that spreads across my 4-level nested collection. And what was really wonderful about it is that once I went through the process of creating my 4-level nested collection, which was quite complicated, and I didn't get it right the first, second, or third time, and then once I wrote the code to populate the collection, getting information out or querying the contents of my collection was very, very simple. For example, is the top sales program overloaded? Well, go to the top sales location in my list of program names and find out how many overloadings I've got. So L programs is a 4-level nested collection. This particular named program brings me down to my second level of nesting. These are all the overloadings for this program. If I have more than one, my program is overloaded. Is the second overloading of top sales a function? Well, go to all the overloadings of top sales, go to the second overloading of top sales, and find out if I have an argument, a position, an argument at position 0. And in the parlance of all arguments, that means that it's a return, not the first argument or second argument. If there's something at position 0, that means it's a return statement, which means it must be a function. What is the data type of the return clause of the second overloading of top sales? Go to the top sales location in my list of program names, go to the second overloading, go to the return clause, that's location 0, and then get the data type at that level. Now, I'm not expecting you to understand these magic values in all arguments. That was part of the problem with me learning how to work with all arguments. Don't worry about that. The point is that instead of writing lots and lots of code, iterating through multiple levels of nesting, I can answer a complicated question with a very simple, trivial piece of code once you sort out the magic values and the parsing of this kind of logic. And now it's all taken care of for me because all the intelligence is built into the data structure itself. Now, again, the point of these slides is not to have you fully understand the utility I wrote to check for overloading. It's a lot of code. Like I say, it took me 90 pages just to explain how I did it. What I wanted to show you in these slides is how you can move from a very complicated world in which you're writing tons and tons of code because the underlying data structure choice was wrong, and instead say to yourself, wow, no, that's not good, I don't want to go there. Reevaluate how you've constructed your data structures. Come up with a normalized approach inside multi-level collections, and then find that the resulting code is much simpler than it would have been. Draw some conclusions. The multi-level collection is a powerful but obviously very complicated feature. The more levels of nesting, the bigger the headache you will have trying to understand how to do the nesting and then write the code for it. But used correctly, it can hide complexity in the underlying data structures and simplify your algorithms, your code. So get the database design right. That can be complicated, but also usually fairly straightforward, certainly if you're used to normalizing database tables. And then the resulting code is much, much simpler to write and certainly simpler to maintain. So again, if you find yourself saying it shouldn't be this hard, you're almost certainly right. It shouldn't be that hard. It's not that the challenges that you have to tackle aren't hard. Business requirements can be very complicated. But it doesn't mean that the code that you write should be that complicated. And multi-level collections could be a great way to help you simplify your code.